All right. Hi, everyone. Welcome to this meeting of the Container Brigade. Before we get started, I was asked by David Oswald to pass on a few reminders. One was that if you haven't yet registered for a RCORD build, please do so register. I did post a link in the Brigade channel on Slack, so please feel free to register for that. It's in the Bay Area here, so for those of us in the area, should be hardly any trouble. Also, there is a link in that channel as well for a call for participation. So if you have an idea around RCORD and containers or anything really related to RCORD that you want to present at RCORD build, please sign up, because they're sooner or later they're going to close both. So the sooner you get signed up and get your idea out there, the better you are. And those are the two reminders. So today, what Kent Hagerman's going to present on Spanneti, which was a container that we used in our demo, what we called reactive programming demo. So this was re-envisioning some aspects of RCORD on Kubernetes. And so one of the main components of that demo was this reactive network programming or chaining container. And Kent is going to present on that. Kent, are you ready?
I believe so.
Okay, I just got to find you and then make you presenter. There you go.
All right. Can you see?
Yes.
All right. So this is generally going to be a deep dive into how Spanneti works and a little bit of its technical design. And I'm hoping that this could be more of a discussion about where we want to go with networking, as compared to purely, like, as much as this is a demo from my side, and this should kind of be taken as an example, and what I'd like to get out of this is what direction we should go from here. So for Spanneti, the general idea was to throw away what we have on the computes for networking. So the fabric is still the same. It's leave spine, controlled by ONOS, but we got rid of vRouter and the second ONOS instance, the overlay instance. So the point here with the software was basically we want to do everything in a much smaller, more compact way. And after thinking about how to do that for a while, I came up with, well, the containers can have labels, right? So we can store the network they're supposed to have in those labels. And basically just whenever a container is started or stopped, go directly off of the labels for building the network. So just to read down the slide, storing the configuration in the containers. We then run Spanneti, and it listens to Docker and watches the containers and derives the network from that. The network only has to be changed when the containers are started and stopped. And the last piece of this was that where I didn't want to take responsibility for the actual functioning of the network. So I don't want to be passing packets. I want to outsource that to something else. In this case, it's being outsourced all the way down to Linux networking. So why is this helpful? The actual state that we want the network to be in is stored externally and can be managed by the container management system. So we don't have the same information stored in two places, and it also makes this layer much simpler because it doesn't actually have to store that data. It doesn't have to make it reliable. So the other decision was the general direction we go in, right, is to we set up the network and its state, but if something goes wrong, if something breaks, we want to be able to react to that. And if we restart, right, we don't want to have to reset up the network. So we want to compare the existing network and what the network should be, and only apply a diff between the two. That keeps things functioning more smoothly, and you don't get traffic hits for no reason. So at first, when I was going to design Spanneti, I went and looked at both Docker and Kubernetes networking, and basically tried to figure out if we could do this first with just their networking and see if we could not, I wasn't even trying to write a plugin at the time. I was just looking, can Docker or Kubernetes do this on their own? And basically they can't. They can do layer 3 fairly well. Docker Swarm in particular has very good support for layer 3 networking and completely separate networks. But layer 2 is impossible. So if we want to have a tenant connected through a OLT, through a PON network, we need a layer 2 connection to the VCPE, and that is completely impossible. So impossible that when I went and looked for a networking plugin for Kubernetes and for Swarm, they just couldn't support it. It was too different from their paradigm. So no matter what, we have to go around what they're trying to do. Are there any questions so far?
So you're saying that Kubernetes and Swarm don't support having, you can't have like a VLAN interface or anything like that? You always have to have an IP address on every single port?
So you can have, so you can use a VLAN, but even if you use a VLAN, like you have to put an IP inside that. So you have to have IP traffic on that VLAN. You can't put just pure layer 2 packets on that VLAN. The other thing is that basically everything that Docker Swarm in particular does with networking is designed for layer 3. If you send layer 2 packets, they won't make it through. It'll just see the packet, say, I don't know where the destination is, wherever the layer 3 destination says it is, and it'll just drop the packets. So yes, layer 2 is not supported. Anything else?
Your layer 2 networks, are they always just point-to-point between two containers, or are there layer 2 networks where multiple containers can participate?
So right now my design is point-to-point, but layer 3 is sort of somewhere in the design process, and definitely something I'm thinking about.
But even at layer 2, you could have network multiple containers are on that network, right?
Right. So sorry, that's what I meant. That's also on the table. To definitely have a. Sorry.
Yeah, go ahead.
Yeah, it's definitely, so rather than just point to point, I do want to be able to have layer 2 networks that span more than 2 endpoints. But I'm still trying to figure out how exactly that should be done, because just having a pure VLAN or VXLAN layer 2 network, I'm not sure what the most efficient way to do it is, and I have to look at use cases a bit more. So it's definitely in the plan, but it doesn't work today.
And the one I have like an underlay overlay model, like the network overlay on top of the fabric.
Right. So it is underlay overlay. Spanneti uses VLAN and VXLAN depending what it's connecting to, and so basically encapsulates. If it's sending traffic over the fabric between computes, it encapsulates in VXLAN. So it's sending IP traffic encapsulated in IP traffic. So the underlay is the physical network and the single instance of ONOS that's there, creating the leaf spine.
Okay, thanks.
So this is generally what I came up with for a general design. Things of note here, basically everything comes from Docker. Everything's listening to Docker. So on the top left, Docker is just the know-all, end-all of what containers are running, right? So when a container is started or stopped, it updates the network graph, and the network graph is basically just a collection of container networks. There's nothing fancy about it. It's not actually building the network. It's just collecting, here's the containers are running and what each of them thinks its network should look like. And then after the network graph has been updated, it sends out events for that particular container. If there's specific link IDs on it, if there's a specific OLT connection, sends out events to the event bus. Those pretty much all get passed over to the resolver, and all the resolver does, its job is basically to compare the existing network graph with the existing Linux network. That's pretty much its entire job. So it just says, what should the graph look like? What does it look like? And tries to resolve differences and set up and tear down interfaces as needed. The remote peer manager does basically the same thing as the resolver. Its only difference is that it's negotiating with peers. So there's a little bit of extra complexity because it has to allocate VXLANs. But it's basically doing the same thing. It's just looking at what does my network graph look like? What does the peer say their network graph should look like? And are there anything that should be connected together? Any questions on the slide? All right. Sorry to mention that, and the other thing is to mention is that Spanneti is designed right now so that it only reacts to changes in Docker. It's possible for a compute node to completely crash and restart, and for all the peers to be unaware. So the reconnect, the fault tolerance there is basically delegated to container management. So if you'd assume that the container manager would see, oh, this compute has failed, it'll move the containers elsewhere, and then Spanneti will react. So even the fault tolerance has been delegated elsewhere, making things very simple. Apparently I'm ahead of myself. I've basically said most of what's on this slide, but just the peers are very separate. They only really communicate to negotiate what should be set up, and there isn't much ping or keep alive between them. I'm going to skip this and go to the demo. So for the demo, we basically have, here's the current tag format. So if you want two containers to be connected, you go in the link section at the bottom and give them the same link ID. So it's whatever interface name you want in that container and a link ID. If two containers have the same link ID, then a layer 2 link will be created between them. The OLT connection is actually even simpler. The OLT connection is simply the Ethernet, the interface name you want, and then the S tag and C tag, just to create, and those will basically translate it into a double VLAN interface, so 2 interfaces deep of VLAN tags. And this will be the example for the demo. I'm going to create 2 containers. One of them will have a single interface, and the other will have 2 interfaces. One of the interfaces in container A will be connected to one of the interfaces in container B, and the other interface in container B is a double VLAN interface. So I'll skip to demo. So here I have a basic pod setup. This is live. This is a real fabric. This is real equipment. We have 2 leaves, 2 spines, 4 computes. This is actually the exact same setup we had at the last demo, if you saw that. So I'm going to work on compute 3 and compute 4. So if I give the logs for the Spanneti instance on compute 3, it's basically just started up. It took a couple seconds to figure out its own IP. No real issues there. So I'll create the first container. You notice here, I'm creating the container that only has 1 interface, and the container is basically a dummy container. It's a small Alpine image, and it doesn't do anything. I put that in the wrong window. Oops. Right. So when I create the container, you see the container is started, and you see an event for that. And you see an event then passing through for that link ID. I just broke that. I just broke my terminal.
Oh.
All right. So container started, we see the event for the link. Because there's only one container with this link, it tries to clean up any connections that existed before. Right now there's none, so nothing happens. Then it tries to link with any remote Spanneti instances. Right now there's remote Spanneti instances, but there's no containers with that link ID running on any of the compute. So basically, the first one comes up and nothing happens. It's just seen by Spanneti. But when I bring up the second one, so very similar, container starts, event. The difference here is we get, it recognizes that there are two containers with the same link ID and binds their interfaces together. So it creates a peer interface and injects the two ends of it into the two containers. And then for the OLT connection, it creates a S-tag and C-tag interface, one on top of the other, connects them to the fabric. So if I go into, let's say, one of these containers, and the other container. So these are the two interfaces we expect in this container, plus the local interface. And same thing in the other container. So if I just TCP dump there, and so the ping won't actually work, but you'll still see our requests coming across. There's a slight delay. It's because of the way TCP dump is running inside Docker, inside, there we go. So we actually have connectivity between these two containers. And it was orchestrated by Spanneti.
So any packet that comes out of the F1 interface on the container
I'm sorry, that was very, you're very choppy. Could you repeat?
So the nature of this link means that any packet that comes out of the F1 interface on the right-hand side container will show up on the corresponding interface 7 on the left-hand side.
Yes, it's a layer. Basically, it's a direct layer 2 link.
It doesn't matter what the MAC addresses or IP addresses are.
Yes, that is correct. Any other questions? All right, in that case, I'll continue. So this wasn't very exciting because we're only running on one compute. So I'm going to branch out. I'm going to kill one of these containers and restart it on the other compute. basically in Spanneti we see all the teardown. If we come in the first container, the interface was actually removed. So all the networking basically all the networking was torn down. So now on the other compute, I'm going to restart that container or create an equivalent container. So notice here we just get this one line on this side. Setup link to remote IP via VXLAN 0. And so we can see the Spanneti instance on the other side. So I see container created. Then it tries to set up a link to the remote, sets it up via VXLAN 0. So again, I see the expected interface is running here, and in this container, the new interface will have been created, as expected. And just to prove that the ping works, seconds, we should get, there we go. So here I have connectivity set up, a layer 2 link between two containers running on completely separate hosts. I guess the last thing I should point out is for the OLT connection, you can actually see the interface they created on the hosts. Well, at least one of them. So the fabric interface is the basically the connection to the fabric, and the fabric.220 is the VLAN interface for 220. That's almost everything I have to show, and almost everything I have to talk about.
So that's
The last thing is that slide that I skipped. So basically, Spanneti is ignoring Docker's Docker's namespace management. So the way Docker separates containers is it creates Linux namespaces for the network, for the process IDs. It creates a number of namespaces for each container and runs everything about that container inside it. In Spanneti's case, it's an exception. It actually runs in the global process space. So this is an option you can enable on a Kubernetes container or on a Docker Swarm container or just on a Docker container. And basically, it gives Spanneti access to the host process space. Spanneti then uses that to break out of its container and manage the networks for the other containers. So it uses that to break it onto the hosts, grab the Fabric interface, and add interfaces onto that. It also breaks it onto the hosts, creates peer interfaces, and injects them into containers as needed. Basically, what this allows to happen is Spanneti is able to reach out and manage the host, but still run completely as a container. Its network is still isolated, so its own network is only used to communicate with the peer Spanneti instances on the other hosts. And so its process is still isolated, but at the same time, it's able to break out of that and make system-wide changes. So this is a container that basically you don't want to have too many of. And by that, I mean, the containers you're running like this, you want to trust them. It requires privileged mode, but it's basically the management for your system. What's nice is you can run all of your management in containers just like anything else, and get all of the benefits of containers. And that is everything I have. Are there any questions? And this can, as much time as we have or want to spend, we can go into a discussion about networking and how it should be done in RCORD.
Hi, this is Charles from Open Networking Foundation. I have a question that you mentioned that right now Spanneti only support the connectivity between containers. Is there any plan to support external connectivities in the future, like connectivity to the internet?
Yes, connectivity to the internet is actually sort of my current task. I've only spent about a week on it, so it's not close to working. I've been talking to a couple of people in the ONOS community about how I can have a movable IP in the fabric. Right now, if you want to route something in the fabric, you're basically stuck so that you can only route to one compute, and you have to do a whole bunch of reconfiguration in order to move that IP. I'm basically talking to them, trying to figure out how to do that, how that's possible. At the same time, there's a question of how much should Spanneti itself actually handle. And by that, I don't mean Spanneti will never handle this. What I mean is more, Spanneti might be broken down into multiple projects. One that's specific to linking containers together, one that's specific to connecting to the internet, and one that's specific to connecting to the OLT and PON network. And that way, if you don't need any one of these pieces, you don't have to run that container, and it just stops Spanneti from becoming that thing that does everything, which very quickly becomes bloated, and you're not really running containers at that point. You're just running one massive container that does everything, right?
Yeah, okay, thank you.
Any more questions? Any comments or?
Do you have any thoughts on the advantage in this kind of decentralized model over the approach that's used in RCORD today, where you have the centralized on-off with the VPN application provisioning similar kinds of connectivity? Like, what's the advantage of using the decentralized model?
So the main advantage of the decentralized model is that every compute can look the same. You no longer have to have a head node. In our particular deployment, hopefully within the next couple of weeks, we won't actually have a head node. We have one or two applications that are actually stuck on a particular node. But moving forward, we're trying to decentralize it so that any node can fail and it doesn't matter. Everything else just migrates to other nodes and keeps running.
And when you say tied to a specific node, that's tied to a node's capabilities, such as a manager node or on every node. Is that accurate?
So if you want to have a node that's particularly a manager node, you can. I know that Kubernetes itself requires, I think, 3 nodes that it sort of thinks as the main manager nodes. But you don't really need to be tied to that. Like, as much as possible, you want it so that the container management system can just move traffic and containers and like wherever capacity is available. So I'm not sure if that exactly answers the question.
Well, you had mentioned that within a week or two that we'll have containers that are tied to a specific node. I was trying to understand, have you expand on that, why they're tied to a specific node and how they're tied to a specific node. Because the issue being, of course, say, oh, they're tied to a specific node. What makes that not a head node, right?
Right.
That's what I was trying to tease out, if we're tying things to like a manager, a swarm manager node versus anything else.
Sorry, there's a slight disconnect between how things actually are and how I think they should be, or how they will be in the future. In general, we want it so that we can move anything, anywhere, anytime. Right now, we have two issues. One is that Kubernetes requires manager nodes, which are sort of a head node for Kubernetes, but it's only Kubernetes, and it's fault tolerant on its own between those nodes. So it's not quite a head node because you can fail over between, say, 3 manager nodes, right? And one of them can fail and it can keep running. So you're not tied to one specific node. But in general, even that is bad for failover, because if for whatever reason you lose those 3 nodes, you're done. And you can't fail over and use what you have. So the best case is to be able to fail over as much as possible from anywhere to anywhere. And that's the design I've gone for with Spanneti, where any node can fail and it will keep running. And any node can come back and it will keep running. CORD itself right now is very much tied to a head node. And to the point that there's specific things that only run on the head node, and if the head node dies, or in some cases, even if it just restarts, it's done. It can't run. Basically, it just crashes the system and doesn't work anymore. And it's basically a question of how far from that can we get as possible. How far can we get from the worst case, and how close can we get to the best case? I think I've said too much about that already.
Kent, about the availability of the control plane of Kubernetes. I suppose you have looked at the Hypercube in Docker solution. There is potential there to be able to have the control plane anywhere with Hypercube, especially running as a Docker container. And then you can use Docker's inbuilt mechanism itself to restart if the control components fail, the API server, the controller, or the scheduler.
I haven't heard of it. I haven't looked at it. I haven't actually heard of it before, but I definitely should go take a look at it.
Yeah, so Hypercube, so very briefly, Hypercube is basically one binary with all the client and the server code built into a single binary in Kubernetes. So the kubelet kubeproxy, the scheduler, API controller, and the API server all are built into a single binary. So if you want a specific flavor of the control plane, you basically launch it with a specific set of parameters. What they have done is they've gone a step further and containerized Hypercube, because it's just a Golang application, a static Golang application. So what that means now is that you can actually launch each of these control components as containers. And if you use something like Compose with these control components, you can build in restarts on failures. And that means you can have your Kubernetes control plane as running as containers that are automatically restarted on failures.
Right. So in general, so even in our pods, the containers that are Kubernetes are restarted on failure. What I'm specifically talking about is when they fail. Like for the duration of time that those nodes are offline, you can't restart. You have to wait for the node to reboot and for it to Docker to come up and for the right. And for that time, you lose it. The other question is if you permanently lose those nodes, if something goes horribly wrong, you have like real serious hardware failure. Again, you're done and you can't recover. But if you deal with that at the software layer instead, then you can. That's not quite the right way to phrase it. If you are fault tolerant enough, you can migrate even the control for Kubernetes between hosts.
Right, and that's where composing them and running them as containers themselves probably makes it a lot easier.
Right. So it's kind of a step in the direction of I want to run as much things as containers as possible, right, so that if something goes wrong, well, I just kill that container, spin up a new one. The one story that's not well handled, I think, by Docker, by Swarm, by Kubernetes, by anybody, is what do you do with data failover? So if you have data like working state in a container, and that container dies, either you have to have that replicated somewhere else already, or you have to just restart from no state.
Right. Yeah.
And so that right now is the hardest problem. With Spanneti, I basically outsourced it and said, well, whatever containers are currently running, that's the real state, because if a container isn't running, I don't care what its state is. I don't care what network it thinks it's supposed to have. It's not running, it doesn't matter. And that was the general design I went with.
Yeah, I view data failover as not a container specific. You're right about the state being stale, but I don't view that as a container specific thing. Even for non-container based applications, the data failover is a problem, especially if the state is in memory.
Right. So that's usually handled with etcd, I think it's called, or yeah, there's a couple databases that can handle it. And so the idea there is with containers, you could have a container fail and basically migrate that single container, and then it starts up with etcd, picks up one of its peer containers and replicates the state from those. So in this case, let's say you have like 3 nodes, right? Any one of them could fail, or they could all fail in succession. And so long as there's been time for the state to be migrated to the new container, you can keep running. I think containers definitely help with the problem, although they don't have a perfect story for it yet.
Right.
It's yet another thing to work on.
Right. I think we might have run out of questions in Menlo.
All right. Any other questions? All right, then we'll close it up. We do want to open source this, and we got to figure out how to best do that within the ONF community. I don't know how that would really work. If we can create a project on the Garrett for OpenCord, or just put it in GitHub and manage it that way. We need to figure that one out. At minimum, we'll make the code available that people can look at and leverage and use. Just got to figure out that exact mechanism we're going to do that with. Gopi, you're gonna, well, first of all, Kent, thank you very much. And Gopi, you're going to post the presentation when it's completely recorded?
So, yes, I'm recording this. I'll transcribe this and post it on the YouTube channel for RCORD, and I'll post it on the Slack and the forums.
Excellent. All right, thanks everyone showing up. And if you have any questions, please post them on the Slack channel, and we'll hopefully get those answered. And again, a reminder to sign up or register for Core Build. All right.
Awesome. Thank you.
Bye.